Okay, let's now see atmosphere in radiative equilibrium. So the atmosphere of a star is simply transporting all of the energy that flows through it, which is produced in a core. Without sources or sinks, the energy is rigorously conserved. So we can write for the atmosphere that d dt is equal to 0. Now, this is also the luminosity of the star. That means that if you are at the core where you have energy production, the dt is not equal to 0. But the atmosphere is not producing energy. Now we can relate the above equation to the flux using the definition of the flux, that dE is equal to flux times the area over the time. Now if you divide both sides by dt, now if you integrate over the whole area of the star, and if you use Gauss Theorem, now this is the integral of the divergent of the flux. Now since the dt is equal to 0, then the integrand must be 0 for all volume elements. What we have then is that the condition of radiative equilibrium is that the divergent of the flux is equal to 0. Now, if you combine this with the plane parallel approximation, where the quantities are only varying in the z direction, this is a simple situation. You simply have that df dz is equal to 0 as for the plane parallel approximation. Well, that means that the flux is constant. That means the volumetric flux is constant. Now we can define this in terms of the luminosity and the radius of the star. And we can also use Stefan Boltzmann law to define an effective temperature for the star. The effective temperature is the temperature of a black body that emits the same volumetric flux. Now, even though we cannot always approximate an emitter by a black body, we can always define an effective temperature. You get the flux, and then you assign the temperature that would give you the same flux. That's the effective temperature, the temperature of the black body that would give you the same flux. Now, having found the solution for the flux, we can go back to the equation of radiative transfer to further constrain the problem. So that's the equation of radiative transfer. Let's integrate this in solid angle. This becomes... Now, since we are in radiative equilibrium, we can assume that the source function is isotropic and take the source function out of the integral. So this integral here, the last one, gives you 4 pi. That's the integral in all solid angles. This integral, the first one in the left-hand side, is the mean intensity times 4 pi. And this integral on the left-hand side is the flux. So what we have then is, now let's reinstate the frequency subscripts. Now the condition of radiative equilibrium, df dz equals 0, involved the volumetric flux, while this equation in here has the specific flux. So let's integrate it in frequency. If you multiply both sides by kappa rho and integrate it in frequency, the left-hand side is the condition of radiative equilibrium, so that's equal to 0. Therefore, this right-hand side is also 0, and we find the result. Now, if you recall the definition of the source function, which is the emission over the absorption, the emissivity over the opacity, we can rewrite this equation then as, this is an interesting result. The right-hand side is the direction integrated volumetric emission. That means the emission in all directions and in all frequencies. Now the left-hand side is the direction integrated volumetric absorption. Remember, the absorption is opacity times the intensity. You integrate that over direction, and you have the mean intensity. Integrated in frequency, you have the absorption in all frequencies. So what this equation here is telling you is that the emission, if you integrate in all directions and all frequencies, is going to match the absorption integrated in all directions and all frequencies. Absorption is equal to emission. This is a statement of conservation of energy. What is emitted in a wavelength is absorbed in another wavelength. how does that play out in the actual spectrum? You see, for instance, here, that the spectrum does not follow a precise blackbody curve, and not only because of the spectral lines. If you pass a blackbody curve with the effective temperature of the sun, you see that it matches here in lower frequencies, but you have a surplus in the visible and a depression in the UV. So what is going on here? You have that the volumetric emission is equal to the volumetric absorption. You have energy that is being absorbed in the UV and is being reprocessed and then re-emitted in the visible. The same thing happens, for instance, on the Earth. The Earth absorbs the visible light from the sun and re-radiates it in infrared.